progesterone, okay? So that this would be used in correct and prompt diagnosis. So that is the only thing I want to tell in this moment. It's really good to being here on this biosensing course. So you mentioned, for example, lab on a chip testing. I don't know if you know Hector Pool, Dr. Hector Pool.
Sorry, I don't know. I'm sorry for my ignorance.
No. He's also a doctor from nanotechnology engineering, and he introduced that topic once in a blue moon. But he introduced that lab on a chip and organ on a chip topic. So it's kind of bit familiar, but I'm looking forward to learning more. Yeah.
Fantastic. Very good. Very good. Yeah. Thank you. Thank you. Thank you, Isai Flores. Thank you. Miriam Cepeda, please.
Yeah, I'm Miriam Cepeda Servín. I'm finishing the nanotechnology engineer. And I don't know what more to say. I'm doing prácticas.
Prácticas profesionales, okay.
Yeah, that's all.
Hey, una pregunta. I have a question for you guys. Where are you doing prácticas profesionales?
¿Cómo?
¿Dónde usted haciendo de prácticas profesionales?
La empresa se llama Johnson Matthey.
¿Perdón?
Johnson Matthey, Matthey, algo así.
Esa es una empresa.
Ajá.
Sí. Ok. ¿Todos ustedes trabajando en una empresa para prácticas profesionales?
Yo sí.
Most of us, yes. Most of us.
Qué bueno. Muchas gracias, Miriam, y bienvenido. Muchas gracias. Sí, Carrillo Guzmán.
Yes, I'm studying a biomedical engineer. And nowadays I'm working in a hemodialysis clinic. And I like this diplomado because I think that I can develop something in my work. So that's all.
Very good. Where are you performing this hemodialysis work?
¿Cómo?
Where, please be, where are you performing the hemodialysis work? In which place?
Se llama Servicios de Salud. No. Sí, Servicios de Salud San José.
Ok. Qué bueno. Sí, es perfecto. Thank you. Thanks a lot, Carrillo. Citlali Guadalupe López. Citlali Guadalupe. Okay. Aranza Lisbeth Martinez Galvan.
Yeah, hi. Do you hear me well?
Sí, yes, perfect.
Okay, hello, I'm Aranza. I'm a biomedical engineering student. I'm not working yet since I'm in the last year of university, but I'm interested in the development of biosensors. And I'm just working in a step-up development project with entrepreneurs. And that's all. Yeah.
Okay. Very good, Aranza. Thank you. Jose Valentin Arroyo Martinez.
Yes, my name is Jose Valentin Rey Martinez, and I am also nanotechnology student. I am so in my last semester of the career, and right now I'm in as an intern of environmental industry.
Oh, very good, very good. Thank you, Jose Valentin. Sergio Trejo Villegas.
Hi, my name is Sergio, and I am studying nanotechnology in the last semester of my career. Uh, I am doing my internship at CIDEC.
At
And
CDEC?
CIDEC,
Okay, CDEC.
ajá,
What is that? Is it a company?
yes, it's Centro de Investigación y Desarrollo CARSO.
Desarrollo, perdón, ¿qué?
CARSO,
Carso, what is that Carso?
it's un conglomerado de Condumex.
Condumex.
Ajá,
Ok. Todo está disponible en Querétaro, todo, cosas. ¿Está en Querétaro?
yes.
Mm, qué bueno, qué bueno. Very good, Sergio. Thank you, thank you. Jesús Humberto García Ramos.
Hi.
Hi, Jesus. Yeah.
Hello, my name is Jesus. I am from biomedical engineering. I am studying in the last semesters. That is why I am in this diploma. Um, I think this module is called sensors. The
Okay.
truth is, um, I think I am very familiar with it, but I hope to learn or understand
Mhm.
how they work.
Okay.
Um, finish.
Very good, very good. Thank you, Jesus. Thank you, thank you. Enrique Enciso.
Um, ¿Sí se escucha?
Sí, puede escuchar, sí.
Okay, I'm Enrique Enciso Lopez. I'm studying the nanotechnology engineering, and I'm not in this moment in practicas, but I hope in soon I get one. And I don't know. I'm expect a lot of this module because the topic is interesting for me,
Mhm.
and I hope it, it
Very
could
good, very good.
be sí, pues,
No, very good, Enrique. So I hope we will deliver really good matter, good information for you guys, so that you can expect something great and expect some important information from us. Very good. Thank you for motivating us also, and giving us a target that we have to give something very critical and important to you all, so that it is very so that you don't go empty-handed. That is what our aim should be, and it is actually. That's what we would like to do. Thank you for this motivation, Enrique. Then Rodrigo Solis. Yeah. Oh, it's fine, Rodrigo. Thank you. No worries, no worries. And Luis Enrique Garcia Montalvo. Luis Enrique. No. Okay. Francisco Josue Porto Suarez. Hi, Francisco. And what are you doing in IBM? No, ¿usted qué haciendo en IBM? No, no entendí. De cosas que usted puso aquí, Francisco Josué Porto Suárez, IBM. Oh, yo pienso que es empresa IBM. Oh, qué bueno, qué bueno. No, está bien, perfecto. Muchas gracias, Francisco, y bienvenido para este grupo. Denis Ramos.
Hi, my name is Nis. I'm a student of biomedical engineer, and I don't know what is the other question because I just entered. I have a issue with my home.
Sorry, you have an issue with what?
With my home, fuga de gas. So I'm a little distracted today. I'm sorry.
Distracted today. Okay. See, I hope you will not be distracted much after listening to this session. Please try to have this better motivation that the subject which which I will be teaching you will be really helpful for your career in future, and I hope this should transform little bit of your enthusiasm. That means, I mean to say, the enthusiasm levels must be increased. So Dennis, thank you. Thanks a lot for
It's not
you
about
attending.
the enthusiasm. I just have a issue with my home, and the stone is throwing away gas. I don't know how to say it in English.
Está bien en
So,
español, está bien, Dennis, está bien en español, no hay problema.
tengo una fuga de gas en mi casa, entonces estoy un poco preocupada. Por eso no es que no me interese la clase, sino que
No, está bien. Usted puede primero, no, clase está bien, que tiene recording de clase, no hay problema, pero usted quiere resolver esta situación para ti, porque es muy crítico, no puede atender la mañana después. Vida es muy importante, crítico. So, está bien, gracias, Denis, no hay problema, ¿ok? Cuidado. Ok, muy bien. So, I hope everybody is very much interested in the aspects which I'm going to start here. The thing is, we are aware of different aspects of organs. We are aware of different aspects of the tissues, cells, all right? So now we would like to give, so now these are the aspects, these are the things which I would like to work on, I would like to discuss with you guys. There was a scientist who said that cells are most critical functional units in the body. Without cells, we cannot be able to form a complete organism. So cells are the functional units, and they are responsible for complete formation of the organism. And this fundamental aspect of cell, people try to understand this later when they started working on individual cells and their different aspects of growth, morphology, and how DNA works, how protein works, etc., etc. So then they started working on those lines. So I would like to start with that aspect, how cells have been useful in development of complete organ. So let's start with that. So I'm sharing with you a lecture on. Oh God, okay. Yeah. So here we have okay. So there were three people who won the Nobel Prize in the year 1968. 1975, sorry. They won the Nobel Prize in the year 1975. And they were David Baltimore, Renato Del Becco, Howard Martin Temin. To give you their background, I would like to tell here that Renato Del Becco was a physicist. And he won the Nobel Prize in the field of viruses, in the field of physiology and medicine. So when you, there was a famous saying, there was a very famous important information which was given few years back, many years back, that if you want to learn, if you want to understand physics, you need to know mathematics for sure. But if you want to understand chemistry, you need to understand both mathematics and physics to understand properly the chemistry part. But if you want to become a biologist, you need to understand mathematics, physics, as well as chemistry, so that you need, if you are a real biologist, I'm not saying that, okay, nowadays there are many biologists who don't even want to go to read mathematics or to understand mathematics or physics. I'm not talking about them, but if you're really interested in biology, the most important aspect is you need to understand all these three subjects so that you are very much capable of, understanding each and every aspect of biology. For example, when you talk about DNA was developed by, discovered by two people. Of course, there were many people before, but the people who received the Nobel Prize was Crick and Watson. When you say Crick, Crick was the person who was a physicist, and Watson was a virologist. He was a molecular biologist. So Watson, J.D. Watson, he received the Nobel Prize along with Crick, who was a physicist. But then Crick was a person who used to do a mathematical modeling of DNA. Okay, and then he developed a 3D model and how these stable DNA structures are formed, bDNA, aDNA, and zDNA. All these structures are formed, how they are formed and how they are stable, and what's the distance between two nucleotides. So he identified that, and how many nucleotides there is a turn. All these is a physics part, not just the biology part. So that was done by Crick, and this is the reason that both J.D. Watson and Crick, they received the Nobel Prize in the year 1962. But then in this case, David Baltimore, Renato Del Becco, and Temin, all these three guys, they were awarded for their discoveries wherein they were interested in understanding how tumor viruses they get inside the cell and how they multiply inside the cell. That was one aspect which they discovered. Then David Baltimore, he also discovered drugs or medicines against cancer. So there was one medicine which is given even now. It's known as tumor necrosis factor alpha. Now, when you're talking about tumor necrosis factor alpha, this particular drug is being given for the cancer patients so that they can survive for their cancer. So then this particular aspect of cancer was resolved partially by David Baltimore, but yes, it could not be resolved completely because there are many problems associated with cancer. Is not a one single issue. It's like a multitasking or multi multi-pronged problem which is there. It's not just biology, it's not physiology, it's not molecular biology, it's not cell biology. There are many things coming together. It's not just immunology. So there are many things which come together to have this problem existing in this world. So let's talk about the history of cell culture. It's very, very simple. So in 1885, Rox, he was the person, he was developing this, how to grow the cells outside the body. So he just isolated some cells. He used to get some cells from animals, from even dead human beings. He was trying to, his job was only one thing, that is to, he used to get the cells outside, and then he used to put in a flask. You know, it's a flat shaped flask, and then he used to grow the cells into it, and that too he used to put different kinds of medium into it, some growth factors, some blood, sometimes blood. He will put some plasma or sometimes serum. So he will try many other aspects so that he can just grow the cells inside, and that's what he was successful in finding out, that what kind of bottles he has to choose for growing the cells. So that's the reason there is a bottle known as Rox bottle. Rox bottle is famous even now. People, everybody all over the world, people who are working on cell culturing, they're using these Rox bottles, which has been made by, the design has been made by Rox. Then in the year, in the year 1907, Harrison, he developed how the nerve outgrowth happens. He was just studying that the neuronal growth. Then in the year 1952, Gay established HeLa cell lines. Okay, so HeLa cell lines were the first cell lines which were developed properly in a proper fashion by Gay in the year 1952. Then in the year 1955, there was a person known as Eagle. Eagle, he was the man who developed a medium for the growth of the cells. Till now, we were not knowing, till the year 1955, people were not aware of that what kind of medium needs to be developed so that the cells can survive. But in the year 1955, Eagle came up with this idea how to grow the cells. Then in the year in the 60s, late 60s and 50s, Delbecco, who got the Nobel Prize, he was interested in finding out how the viruses, they get inside the cell, and they affect the genetics of the cell. So he tried to modify the medium, Eagle's medium, and then he tried to grow the viruses inside such cells. And then in the year 1961, Hayflick, he tried to understand how the division of the cells take place. Then in the year 1964, there was another guy who was talking about somatic cell hybridization. That is how two cells, they form a proper hybridization in this case. So this was all developed by Littlefield. And then 1965, Ham, he started growing the cells, cloning the cells outside the body. Then in the year 1976, Sato, they had injected in the medium, they added some hormones, some growth factors, so the cells grow perfectly. Then in the year 1977, there was Wigler and Axel. These two guys, they helped in the transfection. That means how DNA will be injected inside the body, inside the cell, how the transfections can happen. And 1986, then they started, having this mouse embryonic stem cells. So now they started doing embryonic stem cell job. And 1998, then they started doing human embryonic stem cells. Till now, even now, people are doing this embryonic stem cells, and they are growing different kinds of, out of these embryonic stem cells, they will make neuronal cells, they will make skin cells. They're not that successful in doing this job so effectively, but at least skin cells have been made, but other cells are difficult to be made. And but yes, people have done almost this kind of work, that through the endothelial, through this stromal cell, they could easily find out what is the status of the cells here. So in this fashion, this is the history of the cell culture. And now I would like to explain you that what is cell culturing. Guys, I have a question for you. One second. Yeah, I have a question for you guys. What do you mean by 2D cell culturing? I think Isai must be knowing a bit about it. What do you mean by 2D cell culturing? Sorry. Anybody? Anybody who is aware of 2D cell culturing?
Sorry, can you come again?
I'm asking you what is 2D, two-dimensional cell culturing? Anybody? Anybody is aware of 2D, two-dimensional cell culturing?
The one that it's done in these Petri boxes?
Petri dishes, yes.
Uh-huh. That one?
So what is, yes, but what happens in that?
We add agar-agar to that thing? No, that it's completely different, right?
Yeah, that's a bacterial cells. If you want to grow, then that's possible. But when you say human cell or mouse cells, animal cells, eukaryotic cells, then it's known as. So what do you mean by 2D eukaryotic cell culturing? Anybody?
Not familiar with it.
We can only grow a layer of the cell.
No worries. The thing is, you know, when you talk about 2D cell culturing, means what? When you are, okay, you being engineers and physicists, you know what do you mean by 2D? Two-dimensional means what?
What?
What do you mean by two-dimensional? What do you mean by three-dimensional? What do you mean by zero-dimensional? What do you mean by one-dimensional?
Width and length of the X and Y.
I cannot hear you, Jose. I'm sorry.
X and Y dimensions.
Very good. Yes. Very good. So the growth takes place when you say zero dimension, that means the growth is not taking place in any dimensions. It is just located on a site. But when you say one dimensional, that means the growth is taking place in one of the dimensions, that is X, for example. So it grows only in the X direction. It doesn't grow on the Y direction at all. Okay, it will not grow. Oh, sorry. Yeah, where is it? Where am I stable? So it will be on always in one direction. All right. It will be one. I will remove this. Wait a minute. Sorry. Let me check like this. This is better. Yeah. So when I say that there is a low dimensional thing that one dimension thing, that means there is an X wherein in X direction means it grows in one particular dimension, and in all other dimension it will not grow. It will not move in any other dimension like Y or Z anywhere. It will not grow anywhere. But when I say two dimension, that means the cells will grow in X dimension. It might grow in either Z or in either Y. So any of the two dimensions, it will grow. All right. Like I should say X and Y. It will not go Z. I will just see Z at the bottom. It will not grow in the bottom. Okay. So it will grow X dimension and it will grow Y dimension. This is the idea. But when I say three dimension, that means it grows on X, it grows on Y, and it grows on Z, and all the dimensions. So this is why I'm showing downwards, because you will have the medium. The medium, I'll show you the medium. I'll just wait a second. Just giving you the cell culture plates and showing you that. Okay, I can show this. So here, share screen, and this is the main. Can you see this, guys? Friends, can you see this?
Yeah, we can see it now.
Oh. So this is the two-dimensional medium wherein you can see this is the medium, the red colored medium. It's known as DMEM. Okay. Delbeco's minimal Eagles medium. This is what is known as DMEM medium. And this particular medium has got like x-axis and y-axis. So in these two dimensions, the cells will be growing. All right. But it will not grow at the bottom. Okay. I cannot expect anything on the top, of course, because there is no medium. But at the bottom, it will not be growing. Or the second option is it will be always at the flat surface. At the, like I mean to say, it will be at the completely at the bottom. The medium is on the top, and at the base, the cells will be growing. How it will be growing? It will be growing like this, and it will be growing like this. X direction, dimension, and Y dimension. But it will not grow on the top. Why it will not grow on the top? Because they have a tendency, the cells in this particular dimension, they have a tendency to have to form only monolayers. They will not be growing in all the dimensions. Okay. And this particular culture plate will also not allow them to grow on Y dimensions. Okay. Because of this, the hindrance, there might be hindrance, and there is also concept of contact inhibition. All right. So, and moreover, you can see the surface is flat. The surface is completely flat. So the cells, they will not, why the hell they will, like for example, in this class of, in this particular class, for example, if I am, like I mean to say that this particular, uh, I can tell you guys that no, what you do is, you can, for example, you guys can tell me that, okay, you come and teach us in WAC directly. And I can tell you that why we have this facility of Zoom, and I can teach you from here. All right. So I have the flexibility. I have the, I can have the, what do you call? I'm just giving an example. Like I have the flexibility to teach you from Zoom, for example. Okay, this is an example I'm giving you. But then suddenly this Zoom stops working. All the internet goes off from the world. And then I will be forced to teach you to come there into the class and take your lecture there itself. And you guys who are sitting at, maybe you must be doing some work somewhere else, or some work means, I mean to say that you are in your room, or you might be in the college or in the university, anywhere. You might be sitting somewhere, but you are not sitting in the classroom. You don't need to sit inside the classroom. But for example, there is no internet. We are all forced to take a decision that we have to come to this particular place in the university, in the lab, in the office, or in the lab, or in the classroom, and then I have to give you the class there itself. There is only one location, and that is in presential. So this is what this is like now. We don't have limitations. Okay. But when there is no internet, then we are limited. Okay. In the same fashion here also, this particular, wherein I'm providing it a complete flat surface, too much of medium, complete flat surface. So what are we doing? The cells are getting the leisure to grow. All right. And once they grow and they reach to the end of, from this end to the other end of the plate, then they will grow in this direction. Okay. So they will cover up all the dimensions Once they cover up till all the dimensions, I mean to say they will touch all the glass part, then they will decide, I don't want to grow. They have the leisure. Okay, they have the leisure, and then they will start absorbing all the medium from the top and from the bottom, everywhere. So they have the leisure to be there. All right. And they can continuously have the medium. Like for 24 hours, 48 hours, they can have the medium. They are enjoying the medium at all with full flexibility. But imagine that they don't have this much of space. We're providing them with one single channel, very small single channel. All right. So when we are providing very small single channel, or if we are providing them with a conglomerate of cells in the same, I'll show you here. Organoids. Organoid in cell culture. Okay. Fine. This one. So can you see this? Hello?
Yes, yes.
You can see the organoids, right? The one which I have opened.
Yeah.
Perfect, perfect, perfect. So you can see here what has been done. A small intestine has been taken. They have been cut. All right. Intestinal crypt has been cut. And then, there will be, these are the myofibroblast. And they have been added into this particular region, which is also having, this is like having pluripotent stem cells. Now these pluripotent stem cells, they will be forming a spheroid. It's not an organoid, it is a spheroid. It is not a complete organ. Okay, it's not a complete organ, it is a partial organ. You can say it has to be tissue. It's just a tissue. So you're having this tissue here. And this is minced intestinal tissue here. This minced intestinal tissue is growing in the collagen. And this is stem cell with intestinal crypt. They're also growing. And then further, once they grow, then after that, they are grown to a level wherein they are known as intestinal epithelial organoids. Now, what are organoids? Organoids are basically organs, but these organs, they will be grown outside the body. That's the reason the word comes organoids. You cannot call them as organs because they are not inside the body, they are outside the body. So that is the one reason, that is one of the reasons that why I'm saying it needs to be organoid. Next, once it is organoid, then after that, like why is it organoid? Because organoid has got different structures, different cells. All right, different kinds of cells. Now, do you know what is present in an organ? Which cells are present in an organ? Can you guys tell me which cells exist in an organ? Like for example, lung. Lung is an organ. Can you tell me which kind of cells exist in lungs? Anybody? Hello. Can anybody tell me which particular cells exist in lungs? Okay, I can explain.
Epithelial cells.
Sorry, yes, Isai?
Epithelial cells, células epiteliales.
Very good. Epithelial cells, mesenchymal cells, and?
Hasta ahí. So far, so good. Okay.
And immune cells, right?
Okay.
Immune cells like alveolar macrophages, all right? Just want to ask, had a curiosity. Dennis, are you fine?
Yeah, it's better now. I got the problem resolved. Thank you for care.
Oh, very good, very good. Okay, thank you. No, no worries, no worries. Just wanted to, I was curious. Everything is okay in your side. Yeah, thank you, thank you. So the thing is, now these organoids means there will be a mixture of cells, like they are having epithelial cells, mesenchymal cells, alveolar macrophages. Okay, alveolar macrophages, that they are immune cells existing in lung, especially. There is alveolar is lung cells, lung macrophages, lung immune cells, you can say. Then there are T cells and B cells in the lungs. Okay. Okay. Then there are bronchial cells. Okay. So tracheal cells. So these are the different kinds of cells which exist. Okay. And these bronchial and bronchioles and all those cells will be responsible for forming an organ, complete organ. In the same fashion, there is an organoid outside the body, and it will have all these different kinds of cells. So when you start with a pluripotent stem cell, and if you are giving certain factors which are responsible for the growth of the lung, okay, if you have a lung growth factor, stromal factor for lungs, then you have epithelial factors for lungs. If you have mesenchymal factors for lungs, if you have got alveolar macrophage factors for lungs, all these things, all these different kinds of cells or factors will be responsible to form a lung organoid. Okay, so this is the aspect behind understanding how intestinal epithelial mesenchymal organoids are formed, or sorry, or any lung epithelial mesenchymal organoid is formed. All right, so this is what is known as organoid. Now let's go back to the presentation. So this is how organoid development has taken place. So you can see here that people started initially, as you all know, in the year 1960s. People were interested in getting all the medium, etc., etc. But in the year 1907, first sponge cells were grown and to regenerate a whole organism. And then in the year 1944, dissociation reaggregation experiments were performed with amphibian prophorus, and then a complete tissue was grown. Then again, dissociation disaggregation was done with embryonic chick. Then differentiation studies were performed in vitro outside the body to form an embryoid. Then the same pluripotent stem cells were used to at least establish mouse embryos. Then there were like breast epithelial organoids were formed in the year 1987 using this extracellular matrix extract. Then there was like embryonic stem cell line established from human blastocyst. Then, there were like pluripotent stem cells were made from mouse fibroblasts. Then 3D cerebral cortex tissue was formed, gastric organoids were formed, retinal organoids were formed, gut organoids were formed. Then, cerebral organoids were formed, lung organoids were formed, prostate organoids, then fallopian tube, memory organoids, then hippocampal organoids, and finally, you can see snake venom gland organoids. That is the greatest ever development. That is snake venom gland development organoids were formed so that, you can continuously get venom. Okay, that was the motto behind that. Now, what's the difference between a 2D and a 3D structures? What is so special about 3D? I would like to show you. Now, what do you mean by 3D? So as I told you that 3-dimensional means it is grown in X direction, Y dimension, and the Z dimension. So you can see here, there is a 2D cell culturing wherein it's very cost effective. It can be easily manipulated. All right. And all right, sorry. So then there are disadvantages in this. There are many disadvantages. Few of them are that the list of the gradient, that there is a lack of the gradient for soluble factors, because the soluble factors are always present in complete medium. It's a circular plate, right? So you add the soluble factors, and it will be easily available to all of them. So there is a very high surface area. Because of the high surface area, the cells will be obtaining all the different kinds of factors for their growth. So there is, in 2D, there is no competition at all. They will be continuously getting the full width things. Even if you want to add even if you want to add pharmacos, your drugs into it, cancer drugs, they will also be taken up very rapidly by the cancer cells, and they will also die rapidly. Could you understand? So they will also immediately die. So when you use your anti-cancer drug into and add the cell culture medium, you'll find most of the cells will die. 99%, 95% cells will die, and you're getting 100% result. But the same drug, if you add into mice or humans, and if the human takes that drug, and the human being is suffering from cancer, all right? Okay, the same cancer from in which wherein the plates were being added, wherein the plates in each cell culture plate, you had the same cancer cells growing taken from the patient sample, all right? In the plate, you will find in the plates you will find that the cells have been killed completely because of the drugs, anti-cancer drugs. But in the same thing, if you take it for the human beings, they don't die. I mean to say, the cells don't die. The cancer cells, they don't die. All right. So what will happen? Why do you think the cancer cells are not dying? Can you tell me, guys? Anybody? Why do you think the cancer cells will not die equally as compared to the cell cultures in 2D systems? Tell me if there is any answer for this, please. Do you have any answer, guys? Why the
Maybe
cancer cells? Sorry?
maybe the diffusion of the drugs can be lowered by the matrix of the cells.
I'm sorry, I could not hear you. Tell me again.
Maybe the diffusion of the drugs can be lower due to the matrix of the cells in 3D culture.
Diffusion of the drug is lowered, all right. Something else?
External cells of the external cells of the matrix protects the inner cells of the organoids.
External cells of the matrix protects the inner cells of this. I could not understand this. Any?
Yeah, the external cells act like a barrier of the organoid.
Okay. So you mean to say that the external cells okay, external cells. I really could not understand what are these external and internal cells. You are talking about I'm sorry, you're talking about this solid tumors. Are you talking about that by any chance? Are you talking about solid tumors? Sorry. No worries, no worries. I'll explain you that. Fine, fine. So we can, when you talk about this solid tumors, then there is a concept of a problem. I'll explain you what is the problem. The problem is that in solid tumors, there is, I'll share it with you again. Sorry. Where are we? Where are we? Where are we? Yes. Okay. I'll explain you here. Okay. So what happens is in the solid tumors, my friends, the cells are facing some great issues. In the solid tumors, there is a leaky vasculature and the pressures are enormous inside. The pressures are very high. The arterial pressures are very high. And when the arterial pressures are very high, drugs cannot be taken in. Moreover, these tumors might also have ABC transporters. ABC transporters are responsible for efflux of all the anti-cancer drug. So they will be responsible to remove all the anti-cancer drug and they will be as it is. They will stay there as it is. I mean to say the drugs will be released. For example, if a cancer cell has taken up the cancer cells, they will detect inside, hey, this is a cancer cell. This is the drug, anti-cancer drug. I need to remove it. So then immediately there will be a U-turn for that cancer drug, anti-cancer drug, and then it will be removed out of the body. Get out, get lost from this place. You're not allowed in. So this is a mechanism. There is a ABC transporter which will capture all the cancer drugs and then they will throw it out. They'll capture it from inside and then they will throw out. So this is the mechanism of cancer cells. So the most important thing is these cancer cells, they have a mechanism of ABC transportation. Second, these cancer cells, in comparison to 2D, like I mean to say, in 2D systems, the cells can grow enormously. There is maximum uptake and the cancer cells can die easily. But inside the body, the cancer cells will not have complete surface. How it will look like? They will be like this. You can see here, this is an organoid. Can you see this organoid, please, guys? This is organoid, and this is like embedded. The organoids are embedded inside a matrix, inside the gel, inside agar-agar, you can say. So they're embedded inside the gel. All right, and it's similar. It's mimicking the body. Inside the body also, the cells are embedded inside some medium. All right, some tissue, some extracellular matrix. So in the same fashion, here also, the 3D organoids are embedded. And the cells are not exposed. They're enclosed. So only a small portion of the cell will be exposed. Rest all other things will be bound somewhere or the other. It will be completely bound. If you can see this. If you can see this. No. If you can see this. This is a mobile. This is a mobile. Okay, yeah. This is a mobile, and this mobile has got a surface. On the top of the surface, whatever you want to add, you can add. But this, so this is like the surface area, very high surface area. But you can see here, if I want to have, oh God. Yeah. So well, you cannot see anything. Fine. I'm going to say that there is a surface area like this. So this is complete surface of my hand. But if I want only a small portion of my hand which is exposed, I'm going to say here the probability of interaction of the drug will be maximum, but the probability of interaction here, and that too in this crevice, is very less. Inside the crevice is very less. These are the dimensions inside the body. These are the dimensions of the cell. So the cells will be available in this dimension, in this particular channel. That's it. So the exposed area for the cells is very less. And if the exposed area is very less, then there is a problem that, the drugs will not be uptaken, will not be taken up, and then the cells will die. Will not die as easily as they were dying outside the body in the 2D cell culturing system. That's the idea. Understood? And then we have gradients of soluble factors, nutrients, and oxygen based on diffusion through gel or cell aggregate. So now what happens here is in 2D system, there is no gradient. There is no gradient. Here you can see here. There is no gradient at all. Gradient means what? If there is like higher concentration, then little lower, then lower, then lower, then lower. So this is the gradient of the factors. But what is the status in this 2D system? You're adding the medium on the top. I mean to say you're adding the growth factors on the top, and it will be spread out all the directions, and it will diffuse completely, and there is complete availability of the soluble factors throughout the medium. But this is not the case in the body. There is a complete gradient of factors. Okay, so and slowly the cells have to move towards it, or the factors have to move towards it so that the cells can take it up. So it is like a dynamic mechanism, dynamic system is there. But when you talk about 2D cell culturing, it's not dynamic at all. It's not at all dynamic. Everything is available. But in 3D cell culturing, there is too much of dynamism in the system, wherein there are cells moving, and wherein there are extracellular matrices are available. Then the soluble factors are moving towards the cells, and it will grow. It will move towards only those cells in which it is interested in. It will not be interested, it will not go towards that direction when it is not interested at all. Okay, it will not go to the dying cell, it will go towards the upcoming cell. So this is the kind of gradients you will find in this kind of setup. I think you can take a small break here, and we'll just take a 5 minutes break, and then we can start again. Will that be okay? Hello, guys. Will that be okay if we take a small break, 5 minutes break? Hello, am I audible to you guys?
Yes, okay.
Fine, thank you. Okay. Yeah, now I can see your thumbs up. Thank you. Thanks a lot. Thanks. Take a break. Hi, friends. I hope you're all here. Back to the presentation. So here now, when we talk about organ on a chip, the main reason why we are interested in this kind of, so first I wanted to create a background that how cell cultures have been grown and how we are interested in mimicking the body tissues by having a three-dimensional cells, by having organoids, also by or we are interested in having three-dimensional structures wherein which is more mimicking towards the cancer cells. But now what are the advantages? What are the benefits? Why we are interested in doing this kind of exercise, ejercicios, right? Why we are interested in doing this kind of ejercicios or exercise in the case of like in the case of making this organ on a chip very much successful. I hope you're all aware of that there are many medicines, many drugs which have been coming into the market from last many years. And whenever a drug is about to come, whenever a drug is coming in the market, you should immediately understand that it takes almost 15 to 20, 15, at least 15 years for the drug to come into a market, right from day of inception. During the day of inception, right? That means today I have started thinking about the drug. It will take, as soon as I start thinking about the drug, all right, with all my facilities around, all the facilities in terms of basic research, drug discovery, preclinical, then phase 1 clinical trial, phase 2 clinical trial, phase 3 clinical trial, and then there is FDA review, and then after that phase 4 clinical trial. So you can imagine that there is almost homework or hard work of 15 years. It can be more than that also. And you can imagine also that there is, due to artificial intelligence, nowadays, this 15-year or 20-year gap has been decreased to maybe 10 years or 8 years kind of. But when you talk about vaccine, you can imagine we had developed vaccine within a year, within 1 year. So but you can imagine that people did basic research for the vaccine, for COVID vaccine, I'm talking about COVID-19 vaccine. So people did basic research, they did drug discovery, they did preclinical research, and they identified which particular genes are responsible. And then they started giving the medicines to human beings directly or partially to some mice, and then they jumped on directly to human beings. So they came up to phase 4 trial, phase 3 and phase 4 trial directly. They jumped from from preclinical to directly to phase 4 trial. Okay, so FDA also didn't approve. Before FDA approval also, they started sending the drugs, the vaccines, and they started applying onto the human beings. And half of them were applied with the things, and then after that, like for example, Russian vaccine, right? I forgot the name. It's from S. Anybody knows what's the name of the Russian vaccine?
Sputnik.
Sputnik, yes. So that was a vaccine which was applied to most of the Mexicans, most of the people from all over the world. And then after that, after getting all the negative information or negative feedback from the patients, they declared that Sputnik should not be injected after this. Almost after 1 year, they declared that. Okay, all other vaccines could be used, but Sputnik was not. There are many other vaccines also which were not used. There were some Chinese vaccines also. After 3 months or 6 months, they declared that no, this particular vaccine is not useful. There are many cases of allergies or reactions or clotting or etc. etc. Many things happened. So then they stopped others and they were using only one or two or three vaccines. So now this kind of work, this kind of hard work is required, and you can imagine that there are like if a particular drug has been initiated, there is an inception. That means there are, as I told you, there are 10 to 15 years. And after 10 to 15 years of rigorous work in the phase 4 trial, if they get to know that this particular drug doesn't work at all for the human beings, because they were trying on whom? They were trying on cell lines, then they were trying on mice, dogs, horses, all those animals they were trying, but they were not trying with human beings. And as soon as slowly and steadily, when it reaches to human being, there are also samples of human beings. So they will be injecting these drugs into the samples of the human beings. Like samples of the human beings means low, like a poverty zone. I mean to say, they will go to Asia, they will pick up some needy people, then they will pick up some in Africa, they will go to Africa and they will pick up some needy people and then they will inject the drug into those needy people and then they will pay them. And after that, they do, and they make them to sign one document saying that anything happens to you, we are not responsible for that. And the person, he doesn't know what is he signing on. He just signs it and he gets the money out of it and then he moves ahead in life. If he dies, nobody cares because he's coming from a low earning source, a low income source country. So nobody cares. And developed countries, if at all there is anybody who is getting killed, suddenly I mean to say, there are human rights which will come into picture, and then they'll start, talking about situations and problems and the drugs and medicines. They're not good. This company will be banned. Most of the time the company will be banned in the developed countries. If anything of this sort happens, the company will be completely vanished from the country. This is the situation. But these international companies, what they will do, they will go to low income groups and they will attack or they will give these medicines to them. Anyways, but talking about this phase 1 and 2 and 3, why organ on a chip is useful? Because organ on a chip means it is directly growing the cells from the patients, from the human patients or human samples. And not only growing the cells, it will be forming a tissue inside this particular the three-dimensional system, three-dimensional platform. A tissue is formed, and it will be a humanoid humanoid tissue. So if there is a humanoid tissue which is formed, then it is very much near to human beings in comparison to mice, dogs, and etc., other animals. And then once you test the drug inside this organ on a chip, then the results are reliable. Okay, in terms of toxicity of the medicine, in terms of, and even there are many things which we can do. I will explain you in the next slides. So there are many things which can be done in this case for the drugs. So now the most important aspect is we will talk about microfluidics. What is so special about microfluidics? Why we are interested in microfluidics? What is the basics of fluid mechanics? Then special phenomena, talking about laminar flow, diffusion, mixing, capillary phenomena, surface energy, all those aspects. Now, when you talk about microfluidics, we are dealing with anything which is in terms of microns. Okay, when we talk about microfluidics, it is talking about 1 microliter. And 1 microliter is approximately 10 raised to -6. Like it is something, anything which is 10 raised to -6. So that is 10 raised to -6 liter is 1 microliter. So this is what is we are interested in. And how this particular microfluidic is very important, because you can see here the hair which we have, hair on the head or any part of the body, they are approximately 70 micrometer. Then you can imagine arteries or venules or veins, they're also in terms of micrometers. They can be 100 micrometer, 200 micrometer, that will be the size of the arterioles or venules. And then these, so here, what is the advantages of microfluidics is that we will be needing very small amount of the sample. For example, a patient who is suffering from leukemia. So we will be, earlier people used to get the sample um, from the bone, from the spinal cord, and it is so much painful procedure, and they will take out the the cells from the spinal cord, and once the cells are taken out from the spinal cord, then after that these cells will be undergoing I mean to say they will be tested whether there are leukemia cells inside or not. All right. Why? Because in the spinal cord, the leukemia cells will be in large amounts, and that's the main idea why we are interested in finding in getting the cells from the spinal cord and then checking, because the density of the cells will be higher in leukemia inside in the spinal cord. But secondly, what is happening is, in the case of microfluidic system, we can take the cells directly from the blood, because this particular system has got a throughput of very small amounts. It will be detecting even 5 or 6 cells, okay, in 1 ml, or even 3 cells in 1 ml. So this is the amount of like cells which are required for example, you are having 100 cells from the blood, and even 1 or 2 or 5 cells are cancerous. This particular chip can detect it. They're that sensitive. So in this way, you can easily identify a cancer cell. You don't have to do any of the high throughput procedures for finding out the leukemia cells inside the spinal cord. It's very difficult and dangerous. Then what are the phenomena in terms of microfluidic system? One is laminar flow. Anybody knows what is laminarity? Anybody knows what is laminarity, my friends?
It's a flow, right? We're talking about flow, right?
It's what? It's what?
Flow, laminar flow.
What is that?
It's a behavior of a fluid which depends on various characteristics, but yeah, the main characteristic of laminar flow, it's that all the particles from that fluid move into sections which are parallel, right? This is laminar flow, what you're saying?
All right, I will explain you.
Yes.
Laminar flow is a flow of the fluid, okay, in a very narrow channel, and it will move without any turbulence. There is no turbulence. So it will move in a narrow channel, and it will move from one dimension, from one direction to the end, from one end to the other end, and there will not be any turbulence. So for example, there is a horse. The horse will move like this, and it will move straight. Okay. So laminar flow is also like this. So it will move straight. It will not move here. It will not move there. Anywhere. So there is no turbulence in the situation. But when you talk about turbulent flow, that means the liquid will move here and there and then like this, and then it will find roots, and then it will move like this, and the movement of the liquid will happen. So where do you find turbulent flow? Where do you find turbulent flow? Anybody? Turbulent flow is found in sea, in oceans. You'll find turbulence in them, right? But when you talk about, of course, there is turbulence in a pipe, but I would like to exemplify. There is a pipeline, water pipeline, Arcos, Los Arcos, right? So there is a water pipeline, and the liquid will move straight into that. Of course, if the liquid is fully filled, then it will move like a laminar flow. But if at all there is some space left on the top, then it will move with a turbulence. So if you have a liquid which is completely packed, allow the liquid with a full force, the liquid will move like completely in one dimension, one direction. Okay, there will not be any turbulence, and it will move straight from one end to the other end. So it will move zoom like that. So this is what is known as laminar flow. Laminar flow, there is no turbulence in the system. All right. Capillary forces. Capillary forces are those forces which are due to the surface tension. The movement will be due to the surface tension. All right. Diffusion. Diffusion is that concept wherein there is a gradient of the flow of liquid. For example, here there is a what do you call, high volume or highly concentrated system. All right. So this highly concentrated system will have a tendency to move towards other region, and in general, it will try to come up with an equilibrium. So you can see here there was concentrated zone, and there is a partition, and then so the concentrated material will try to diffuse, and they will come out of it, and then the diffusion will take place, and then once the diffusion takes place, then there will be, like, once the diffusion is taking place, then there will be equilibrium between the two, there will be balancing out, and this is what, so this will happen unless, and like, diffusion will take place only unless and until there is balance or equilibrium. If the equilibrium comes up, then there is no diffusion taking place. So diffusion is a process which is dependent on gradient. If there is, so if the levels are low and one is high, then it will supply so many things so that the level becomes equal. So till this point, diffusion will take place. After this, no diffusion will take place. This is the idea. So advantages of microfluidics is low sample reagents consumption. That is the very great example which I told you, and small physical and economic footprint. Then advantages of microfluidics, wherein we have this lab on a chip system. You can see here, there is a lab on a chip system wherein there is sample preparation, extraction of molecules, amplification, purification, control of chemical reactions, surface functionalization, and detection. All these aspects are possible in this particular system. So this is what is known as a lab on a chip thing. Fluid mechanics. Now, what do you mean by conservation? Anybody who can explain me what is conservation of mass? It's a physics aspect. So I think all the engineers must know conservation of mass. What do you mean by conservation of mass? Yeah, tell me please, Isai.
Uh, uh, well, it's a law, and as the energy conserves, also the mass conserves, right?
Yeah, can you explain me that? You're right. But
The same mass, well, I will explain with my own words. The same mass which enters into system should be the same what as it outs, right? As it came out, right?
Okay. Okay. And what do you mean by conservation of momentum? Anybody else? Conservation of momentum? Anybody knows what is conservation of momentum? Okay. Just give me 1 second. Just give me 1 second. I'm just Sorry, this time I had some emergency. I'm very sorry. Yeah, sorry. So now, please tell me, what do you mean by what is this? All right. What do you mean by conservation of mass? Can anybody tell me that? I think Isai explained, but I would like to say that in conservation of mass, mass can neither be created nor be destroyed. All right. It can be simply transformed into a form of energy. Like mass can be transformed into energy and energy back to mass. And so this will be a kind of concept which will happen. But energy mass cannot be created nor be destroyed. That is the idea behind conservation of mass, which is equivalent to conservation of energy also. Wherein you know what is conservation of energy. Energy can neither be created nor be destroyed. Okay, it will be transformed from one state of energy to another. For example, potential energy will be transformed to kinetic energy. Kinetic energy will transform to translational energy. Translational energy will transform to like that. So it will not be or electrical energy or heat energy, etc., etc. So this way there is conservation of energy. No, sorry, mass energy. Yes. What do you mean by conservation of momentum? Anybody? What do you mean by conservation of momentum? Anybody can explain me what do you mean by conservation of momentum? Anybody? What do you mean by that? Nobody can explain what do you mean by conservation of momentum? Sorry? Sorry, I could not understand. Tell me again. Sorry, come again, sir. Come again. Oh, it's like when you play pool. Okay, very good example. Yes. So what happens when you play pool? So you are playing a pool wherein you have one ball interacting with another ball, all right? And if two balls are interacting with each other, all right, so they will so for example, moment is preserved in time, only dispersed. All right. So what happens is the momentum will be conserved unless and until there is an external force applied. So for example, there are two bodies, all right? Two bodies will collide with each other. So one body will will transfer the energy to the other guy, all right? And overall in complete system, the overall energy or the momentum will be constant. Okay. Overall, when, for example, there is an isolated system and there are two balls. Okay. And when one ball, if at all they are just colliding randomly, okay, if they're colliding randomly, they will hit each other. And if they hit each other, I'm talking about not pool. In pool, what is happening is there is a rod and you're providing external force onto the ball, and that ball will be just transferring that energy or the momentum to the next ball. I'm talking about basically two random balls, and there is an isolated system. And so what is conservation of momentum? In conservation of momentum, what happens is there are two bodies, okay, in an isolated system which will be colliding with each other. It might collide with each other, and in that process, it will transfer the momentum from one ball to the other ball, wherein there is no external force applied. Okay, this is what is known as, because if you are talking about external force, then what will happen after that? That there will be, if you want to apply some external force with a rod, then there are like unbalanced forces. Then that ball has to collide with the next one. The next one will collide with the next one. The next one will collide with the next one. So in this whole process, it will collide until and unless and until the whole momentum becomes zero. Okay, that is till that particular moment, your balls will be colliding. Okay, so this is also a pool, can also be an example, but it will be like you're applying some external field. You're applying some external field to have the momentum done. In the case of now, what do you mean by here? Let's go to the when you talk about. Okay. All right. So you can see here, yeah, here. So as you're given, so there is a pool. One ball hits multiple balls, and in such a way that they will transfer equally the energy to all of them. Okay, it can to all of them, or it can transfer the momentum to one guy, and then the other guy will transfer the momentum to the next, to the next, to the next, to the next, and at the end of the day, it will be the momentum is completely conserved in that point, wherein the collision happens, and as soon as the collision happens, it will lose all its momentum. Okay, and till the momentum becomes zero, that till the point wherein there is no moving ball inside your pool. Okay, so in this case you have an external field which is applied. Okay, this is also conservation of momentum. So could you understand, guys, if you don't apply any external field and there is a random ball which are moving in an isolated system, one ball is moving and it hits another ball, so this energy will be transferred to the next one. And for example, if the collision is very high, then this guy will also have a movement, and then it will come to hit the other ball. All right. So this continuously can happen till the moment they become stable. Okay. But in this process, what is happening? There is the momentum is being transferred from one ball to the next one, or from the next one to the previous one. So this will happen unless and until these two balls become stable and they stay there only. Okay, so this is this is where the conservation of momentum comes into picture. So this is what is known as conservation of momentum. Second concept is you play a pool, you apply an external field and hit the ball, and the ball will be having so much of energy that it will hit another one, to the next one, to the next one, to the next one. So it will hit to other balls in such a way, or other balls will hit to the next one and the next one and the next one, till a point wherein they lose all their momentum and the momentum becomes zero. Okay, so what has happened? Momentum is conserved at the end of the day. Okay, it started from where? It started from the rod, and we have put some momentum into the ball, and it started from there till it reached to the last ball, who took away all the momentum and then stabilized itself. So this is wherein that is known as conservation of momentum. There is incompressibility and no slip boundary. Velocity of the fluid flow at a surface is always zero, all right? So I think you all know this about it. And then no slip foundation, no slip boundary condition. Now, what do you mean by that? When, I should explain this here. When you talk about okay, is it possible? I have a question for you guys. Is it possible to swim in water? You guys can swim in water?
I don't know, but yes, we can.
Yes. And can you, then I want to replace that water with honeybee. Will you be able to swim?
I don't think so. The density is much higher.
Sorry? Sorry, tell me again.
The density of the liquid is more higher.
Yes. So what's happening is the Reynolds number, okay? Reynolds number play an important role over there. Okay, anything wherein the Reynolds number is less than 2000, it will be laminar flow. And if it will be greater than 2000, it will be, greater than 2000, it will be a turbulent flow. Moreover, there is one more concept, that the viscosity, all right? Viscosity, there is a what is Reynolds number? Reynolds number is the ratio between viscous forces and inertial forces. Okay, so this is the viscous forces and the inertial forces. So what is happening is, do you know a bacteria? Bacteria, I think you're all aware of bacteria, right? Hello, guys. All right. The thing is, you guys can move in water. All right. Why? Because the viscous forces are very less. And accordingly, inertial forces which are applied by you are also very less. But as you increase the viscosity, or as you increase the viscous forces, okay, as you are increasing the viscous forces, what will happen then after that? The inertial forces which you will apply, okay, it will be terribly high. Okay, the inertial forces, that means the force which you will need to move in water is lesser in compared to the force which you need to move in honeybee or in some kind of oil. It will be very high. So that is the reason your body cannot move. Same thing, bacteria, for example. Bacteria is in the medium, okay, in a agar medium. Agar medium is considered to be, for the bacteria, it is like a stone, like a big rock. Okay, so they will start move. So the bacteria cannot move so easily in that. And now if you want to move, they will have some flagella or something, and then they can start moving, but the movement will be like very difficult, of course. But with the flagella, they will start, first of all, vibrating a lot, and then they will start jumping or moving. And imagine one water molecule will act like a rock for them. It's not so easy for them to move in the medium. So this is what is happening inside, I mean to say, when we talk about Reynolds number. Now, what do you mean by Newtonian fluid? Anybody knows what is Newtonian and non-Newtonian fluid? All right. When you talk about Newtonian fluids, that means, for example, water bottle. If you turn it down, water will come out very easily. Am I right? Am I right, guys? All right. So if water comes out easily, when you move water down, water will easily come out. It will be rapid. But if you take a ketchup, or if you take oil, okay, very thick oil, and you just turn it around, turn it down. Will it be coming easily? No, you have to put force, you have to just press it, you have to do so many things so that the liquid moves down. All right. Otherwise, water, as soon as you turn down, it will move down. But ketchup, if you turn down, it will be like this only. Then you have to, then it will slowly come like this. Then it will slowly come like this. Then it will slowly come like this. And then it will come down onto wherever you want to put this ketchup into your food or wherever. So this is happening when ketchup or so this is the difference between Newtonian and non-Newtonian fluids. Newtonian fluids means water. Water is the greatest example of Newtonian fluids. Wherein water, as soon as you put some stress, there will be equal amount of strain, or there is a strain, there will be equal amount of stress, and it will be equal. It will not be different. But for example, for crude oil, for oil, okay, so you can see here. So the rate of shearing strain and rate of shearing stress is almost similar. But rate of shearing strain and rate of shearing stress is different in crude oil. Okay, so what will happen? The strain is less, like you put a very small amount of strain also, but but it takes a lot amount of time for the crude oil to move towards the gravity. Okay, because it is very viscous. Okay, but when you put water, it will not take much time to come towards the gravity. But for the oil to come down, crude oil to come down, it takes a lot amount of time. Okay, there is a lot amount of shear stress which is required for the crude oil to move towards gravity. So this is the difference between, Newtonian fluid and non-Newtonian fluid. Newtonian fluids are those fluids which have equal strain and stress. As soon as you give strain, there is equal stress on the system. Yeah, like that. Viscosity, I told you, like viscosity is a measure of internal flow or internal friction or resistance to the flow. So here you have air 0.00, 0.017, acetone 0.3, water 0.9. You can see the viscosity. Mercury is 1.5, olive oil is 80, honey is 2000 to 10,000, right? So you can see here, this is the Newtonian fluid wherein strain and stress is equal. Okay, this is the difference between, and non-Newtonian fluids are paint, blood, ketchup, cornstarch solution, etc. Okay, fine. So then when you talk about turbulent laminar flow, laminarity means the flow of the molecules will take place in a channel, in a micro channel, in a perfect fashion. But in turbulent flow, that means the molecules will be moving in different directions, and overall they will be moving in a same way if there is a force applied from the top, and then there will be turbulence in the system, and then they will move, and then there will some turbulence, and then they will move. There will be turbulence, and then they will move, and they will try to move here. They will try to move there. So this is the difference between laminarity and turbulent. In laminarity, the direction of the movement is only one direction, but in turbulent, the direction of the movement is multiple. It's in all directions. Yeah. So laminarity is vectorial. It's vectorial, completely vectorial, and turbulent is non-uniform. Okay, that is the difference between the two. Gout flow is like what happens is there will be a steady flow between two plates. Okay, this is one plate, this is another plate, and there will be steady flow of the movement. This is what is laminarity also. So what is happening in laminarity? It will move steadily towards one direction. Okay, and no slip condition applies. There is no inertial forces required for the movement. It will move continuously and straight. That is what is called flow. Then these are all the properties of laminarity. So what is so there is a concept of Poiseuille's flow, in which there is a pressure driven flow. There will be pressure applied and it will start moving. Okay, like that. So you can see here, there are different colored liquids in a microfluidic channel, and you allow microfluidic channel having different colored liquids to move. All the different colored liquids will not diffuse. They will not diffuse in, they will move straight. They will not go here and there. This is a difference between, this is what is known as laminarity. And as I mentioned, what is diffusion? So this is a high concentration zone, and this is a low concentration zone, and this is a semi-permeable membrane. So what will happen is the particles will move from high concentration zone to low concentration zone, and then there will be a net flow, and then the things will move. Diffusion and mixing. All right. So what happens here is, there is, if at all you want to have the movement of the liquid, okay, so this is this is what is known as laminarity. There are two liquids moving in laminarity, but they are all separated. There are two colors you can observe here. There are two colors being seen. But when you give a turn, as soon as you turn it, what happens is, due to the turn, there is a turbulence which is introduced. And if there is turbulence introduced, then they will be they will lead to diffusion of the one colored liquid into the other, and this other color, yellow to green and green to yellow. There will be little mixing, and then due to the mixing, there will be diffusion of the liquid through it. Then at the end, again it moves, again it will stabilize, and there will be laminarity, and then again it will come back, and then there will be laminarity again. So laminarity will be happening, but during the turns, what will happen is there will be mixing as well as there will be diffusion of the system. So this is a greatest example of diffusion and mixing, wherein you can see here that the liquid is passing, and then you can see here that so for example, there is like this particular liquid moving here, and it's like moving like a tree. It moves like a tree. All of them are separated, perfectly separated. And then at the end of this point, you can see they're all three different colors, but some of them have mixed a bit, and finally you have only three. So you started from 5, at the end of the time you have 3. So some of them have mixed and diffused also. So this is what is happening. What do you mean by capillary phenomena? Now, so what is microfluidics, first of all? In microfluidic system, you're basically dealing with very small micrometer sized channels. All right. It is like it's dealing with micrometer sized channels, wherein you will be having so what happens is, in the body, do you know how many venules are present in the body, arterioles and venules in the body? Do you know that? Anybody? Guys? Friends? Do you know how many arterioles or venules are present in the body? Anybody? There are approximately 3 million arterioles and venules present in the body. And 3 million means how many cells exist in the body? Do you know that? Approximately 3 million cells exist in the body. So you can imagine one cell, one arteriole or one venule. Okay. So that is the situation. And arteriole means they are a very thin pipeline. All right. They are a very thin pipeline that is known as capillaries. There are many capillaries existing. All right. And these capillaries are responsible to allow blood to pass through it. So blood will be passing through that. So through the capillaries. In fact, capillaries, what is the size? It is in micrometer. And that is the reason microfluidic system is mimicking the body. All right. Moreover, you can imagine, do you know xyloma ephloema? Anybody? Xyloma or phloema? Anybody? I'm not getting answer from anybody. Are you listening, guys? Can you hear?
Yeah, we can hear you.
Okay, what do you mean by xyloma or phloema? No? Okay. Xyloma is, okay, first of all, it's in the tree, xyloma and phloema. So what happens is, xyloma is responsible for the transfer of water, liquid, okay, from the roots to the top tip of the leaves. So it is due to the capillary action, okay, the water will move from the base to the top. And what is phloema? Phloema is another pipeline. It's again a microfluidic channel, which is allowing the food from the tip of the leaf to the base of the root. So you can imagine how long these channels exist. Like you can see here, how big these channels are. Okay, these are so big channels which are responsible for the transfer. You can see here, there are microfluidic channels in this, and liquid water will move from the bottom to the top, and for the food will move from the top to the bottom through the phloema. And this is the greatest ever what do you call, world's wonders in the I should say, yeah, it's one of the wonderful things which is happening in nature. Then pressure of the liquid column is delta P is equal to rho GH. Capillary pressure is approximately delta P is equal to -2 gamma upon R. So anyways, this is so how, what is the capillary phenomena? So how the liquid moves up or moves down, it is explaining that. So there is a pressure of the liquid column in the liquid column, so that moves against the gravity, all right, and then it reaches on the top, or it moves towards the gravity and it reaches at the bottom. So there is always some pressure involved in the system. So what do you mean by surface tension? Surface tension is a property of cohesion, the attraction of molecules to like molecules. So here you can see here that there is on the top, there is a good amount of surface tension. And when there is good amount of surface tension, there is a probability that these molecules which are on the surface will evaporate. Okay, so do you know that why, if anybody can explain me, why do you think clothes are getting dried even at room temperature? Do you know why clothes, ropas, are getting dried even at room temperature? Anybody? You have to answer this question. Otherwise, I will not move ahead.
I don't know.
Why do you think the clothes are getting dried even at room temperature? Water, because it has got water molecules, right? So if they have got, yeah, Isai, yeah, please tell me.
I was just thinking on the humidity from the air. Maybe some pressure that it's going on, some pressure stuff going on.
It's a concept of surface tension.
Okay.
What's happening is, on the surface of the cloths, you will have water molecules. All right. Water molecules are throughout, right? Like water molecules inside, on the surface, everywhere. So due to the air, due to the atmospheric pressures, what will happen due to the air or whatever? What will happen is they will take away air, water molecule from the surface, and it will be replaced by the water molecule from the bottom. And then again air will move, and then they will take away the air molecule from it. So that's the reason your clothes are getting dried. Otherwise, you would have kept it at 100. So why, like if you want to boil off water, it takes 100 degrees Celsius, right, to evaporate it. But it's happening at 24, 25 degrees Celsius. Why? It's happening only because of the beauty of surface tension. Due to the surface tension, there is atmospheric pressure from air, and that air molecule will pick all the water molecules, clinch away all the water molecules and move out. All right. And then the base water molecule will be replaced on the top, and then again air will come and it will remove all the top water molecules and away from it. So due to the surface tension, these molecules are removed or evaporated. Okay. Then okay, adhesion versus cohesion. So what happens is you should be very much whenever you're growing a cancer, like anything, so what do you mean by hydrophobicity? Like for example, lotus. Lotus is such a loto is a flower, and the leaf, which is considered to be the very famous concept, is lotus effect. Lotus effect, why? Do you know what is lotus effect?
Yes.
What do you mean by that? What do you mean by lotus effect, my friends? Any answer, please? What do you mean by lotus effect? All right, no worries. Lotus effect means you can see here, this is hydrophobic. So when you have added water molecule, it will stay onto the top. It will float it onto the top. It will not diffuse in. Okay, so when the material is highly hydrophobic, the water molecule will be on the surface and it will not move in. When the when the system is hydrophilic like this, you add water molecule and water molecule will disperse inside, will pierce inside. Okay, that is known as hydrophilicity. All right. So there's a difference between hydrophobicity and hydrophilicity. All right. So hydrophilic surfaces, they will be water loving. Hydrophobic surfaces, they will be water fearing, and super hydrophobic, they will be water hating. All right. This is the difference. All right. I think yeah. Any doubt, guys? If you have any doubt, please tell me till now. Any questions? Because till now we have understood what is the concept of, till now we have understood what is the concept of like what are the basics of microfluidics. Okay, what are the basics of microfluidic system? So when you talk about organoids, they are not microfluidics. They'll be grown like a clone of cells. Okay, it's like a clone of cells, and they'll be grown inside a small well. It's small pozo or well. But when you talk about microfluidic system, it is like a single channel. You can see here that there is a single channel. And in these single channels, the cells will be growing. All right. And when the cells are growing in a single channel, it will mimic the capillaries inside the body. So it will mimic the capillaries, and then this is the way cells will be existing inside this microfluidic system or inside the human body. So this is the difference between, so till now we have understood why microfluidics, what is microfluidics, what are the different aspects of microfluidics, what are the properties of microfluidics. So in microfluidic system, there is no gravity. Okay, there is no effect of gravity. There is no effect of what do you call? So there will be there is no motion. Okay, the motion will happen, of course, but there must be some force which is required. All right. So there is no gravity and there is no this thing I mean to say. Now, when you say gravity, do you think our body is having gravity with us, within us? Do we follow gravity? Guys, can you hear me?
Yes, yes.
Okay, please tell me, Isai. Isai, yes, please tell me whether we have like our cells move according to the gravity in the body, in our body. I mean to say, when I stand, what is the status? When I sit, what is the status? All the cells will go down, or else I turn upside down, all the cells will move up, or all the liquid, all the blood will move up or down.
I should say, yes, there is kind of, I don't know if it's gravity. I may be thinking in another things like osmotic pressure, but gravity, I don't know.
Sorry, tell me again, gravity is there or not? In like gravity is, we follow gravity? Blood follows gravity or not? Yes, yes, I still, don't worry. Tell me. Don't worry about it. We will, like, nobody will kill you. All your answers are well, correct. Don't worry. Tell me, no worries.
Well, the blood flows also goes from down to up to from up to down, so no, it doesn't follow the gravity rules.
Exactly. It doesn't follow the gravity rules. Why? Because it's a non-Newtonian fluid. Okay, non-Newtonian fluids, they don't, the blood is what? Blood is non-Newtonian fluid. It doesn't follow gravity rules. Moreover, blood will move through what? Through a microfluidic channel, like a capillary. It moves through microfluidic channel. And when it's moving through a microfluidic channel, there will be no gravity followed there. Okay? Okay, then any doubts, my friends? If you have any doubt, please tell me. Till now. Please tell if you have any doubt. Till now, whatever you have been understanding, is it okay? Could you understand well? Or anything which you could not understand? Or I'm very sorry, I didn't ask you initially. Could you understand my English? Was I very slow or I was very fast or slow? Okay, thank you, Sitlari. But if you find any problem in understanding my English, please tell me, and I will be slower further. Okay, thank you, guys. Thank you, thanks a lot to all of you. Thank you. Now, my next question is, what are your doubts for today? If you have any doubt, please raise questions and ask me. No worries. Nobody's having any question?
As
All
of
right.
now, there is no question. Yes.
Sorry?
As of now, there is no question. Yes, yes.
Okay, okay. There's no question at all. Fine.
I mean, some physics concepts that we have to study a little bit better. But all good. Yes, all good.
But then these concepts, these concepts which I have taught today, they are like basic engineering concepts and basic science concepts. You must have read this during your high school, or you must have read this during your pre-university things. And because, for example, when you talk about Newtonian, non-Newtonian fluid, you talk about laminarity, turbulence, turbulent flow, or you talk about how how these viscous force, inertial force, Reynolds number play an important role. So these are some of the basic concepts, and I think you must be knowing it, all of you. But I've brushed this idea. Why? Because in the next session, that is tomorrow, when I'm starting with, tomorrow I will be starting with organ on a chip model, especially, and how they are growing the cells, how the cells are grown, and then how these cells stay in that microfluidic channel, and what are the things which we are lacking in, what are the how to measure the cells are viable or not, how to measure the cells are proliferating or not, how to measure the cells undergo apoptosis, they are getting killed out of them. So these are some of the very important aspects when you're dealing with this what do you call organ on a chip. All right. So my friends, guys, I hope you have understood well, and I would request you to please read your basics, read a little bit of basics, whatever I have taught you today. Of course, I will share with you these presentations, etc., or the articles also. But I would request you to please read these concepts well. And tomorrow I will be dealing with exactly what is organ on a chip and deal with some examples of organ on a chip. All right. Okay, guys. I hope you have understood. I hope you have understood well. If there is anything which you could not understand, please tell me tomorrow and I can explain you again. Don't hesitate to ask me. Okay? Please don't hesitate.
All right. Yeah.
I am here to resolve your questions and exploit me as much as you can. That's what I want to tell. All right? Best of luck, guys, and meet you tomorrow, same time, 7 p.m. All right? Thank you. Bye. Take care.
Thank you. See you.
Thank you.
Thank
Thank you. I
you.
appreciate
Thank
it.
you.
Bye-bye.
Thank you, guys. Thank you. Bye. Bye. Thank you. Thank you.